Good afternoon, ladies and gentlemen, and welcome to your SETI Institute Colloquium series. My name is Frank Marchis, and I will be the host for today's colloquium. Thank you very much for coming here today. I know it's been a change of our schedule, so I'm very glad to see that a lot of you receive our last-minute emails and come to hear the talks, these very interesting talks, I guess, on exoplanet. So let me introduce first our speaker. So Barry Welsh is an astronomer at UC Berkeley at the Space Science Laboratory. He got his PhD at University College London, where he basically designed and built a balloon-borne far infrared telescope at 100 micron, if you remember correctly. And then after a postdoc at University College London and a few years at the University of Oxford, he came to the US to work at UC Berkeley Space Science Lab, where he becomes a research astronomer for the Extreme Ultraviolet Explorer project. He went to NASA headquarters for a few years as well, between 1991 and 1993, to become the visiting senior scientist. And today he's a project manager and research astronomer at the Experimental Astrophysics Group at UC Berkeley Space Science Lab. When I saw that Barry was coming to give a talk, I looked at my email because his name looked familiar to me. And I remember that I received an email from him in 2006 that he sent to the list of astronomers at UC Berkeley because he was a famous star at a reality show on Fox TV called Trading Spouses, and which has been here in April 2006, and you can still see it on YouTube. I watched a bit of it. So more seriously, Barry is an extremely famous astronomer in our field. He had 200 referee publications, mostly on the physics of local interstellar medium. He built numerous instruments and used numerous space-based and ground-based telescopes from the X-ray to the far infrared. One of his significant publications is the first 3D map of interstellar gas within 300 parsec, which was published in 2010. Today he's semi-retired, like several astronomers, but he still works a lot. And today he's going to talk about this interesting study of Exocomets around the 8 Abstar that is being conducted with various telescopes. Please join me in welcoming Barry.
Well, I'd just like to thank the SETI Institute and Frank for inviting me to give this talk, and also Microsoft for hosting it. But most of all, I'd like to thank you guys for braving the elements today to come out and listen to me, because quite frankly, I wouldn't come and listen to me. Well, my wife never does anyhow, so. Okay, but most of all, I'd like to thank my collaborator, whose name is Dr. Sharon Montgomery. She's at Clarion University in Pennsylvania, and she's done most of the work with me. Now, this is called Exocomets. Now you see them, now you don't. I'll tell you why I got into this later on, but there's a whole load of things going on exoplanets at the moment, as I'm sure you're more than aware of. But you know, they're just so last year. This is at the forefront at the moment, hence my talk will be short somewhat because we don't know much about them. And also, I know nothing about comets whatsoever. I'm an interstellar medium guy. However, before we get on to exocomets, I think we should at least say something about comets themselves, just so everybody's on the same level field as I am. So everything I know about comets is in the next 20 slides. So if there's any experts, please go away, have a drink, come back. Okay, just to see if you're on your toes. Anybody know which one this is? By the way, this is the comet up there. Yeah. Whoops, it's Hale Bopp. Remember Hale Bopp? Okay, let's see if we can get you better then. How about that one? Anybody guess? Go on, give me some famous comets. Which one? Halley's Comet. Let's see. Yes, it is. 86. Wow. And how about this one down here? Think Japanese. Yeah, Kohoutek. Right. And anybody know what this one is? This only happened a couple of years ago. Nope. It's Panstarrs. Right? Bright, isn't it? Or is it? This is what we took from the Space Science Lab. Can everybody see the comet? Can everybody see this shining thing up there? Yeah, and that's about the only comet I've ever seen, really, which doesn't tell you much. Okay, let me tell you something about a history of comets. They're always, in history, they're always the harbingers of doom. Actually, you don't need the doom, because you can't be a harbinger of anything else but doom, I suppose, right? Can we have the harbinger of Trump? That would be good, wouldn't it? Okay. Oh, sorry, mixing politics with science. So sorry. Okay. And this is how, medieval people, all blight and people dying, and there's the comet in the distance there. Believe it or not, there was a comet in the sky before Caesar was assassinated. So instead of A2 Brute, it should have been A2 Halley, perhaps. Ooh. Bayeux Tapestry, Bill. You can tell from the accent that I think I'm a Brexit Brit from the north of England. And believe it or not, there was a comet in the sky before poor King Harold got the old arrow in the eye, and that nasty Frenchman, William the Conqueror, came over and took over Britain. And just to show you, there is the comet on the Bayeux Tapestry, which is in France, and these are, I guess, poor old Anglo-Saxons. Also, it was comets blamed for the Black Death. The next year was the fire of London. They didn't get blamed for that. It depends which side of the fence you're on with comets, I suppose. Incas, yeah, Pizarro, there was one in the sky there, poor old Atahualpa. And this one's great. Callictus III, he actually excommunicated a comet. Wow, the arrogance, yeah. But guess what? If he'd been Muslim, I don't think he would have excommunicated it, because the Muslims won in the Battle of Belgrade. So, how about cashing in? Let's do a bit of science now. 1908, the Yerkes astronomers found cyanogen in Comet Morehouse. And a couple of years later said, hey, Halley's going to be passing in a couple of years' time, and we're going to go through its tail. But hang on a second. Isn't cyanogen poisonous? So we better protect the public. So the shysters got together and started selling anti-comet pills. What else would you do? And they put all these warnings up. Close your windows. The comets are arriving. Poisonous gas will get you. And if you still think you're safe now because, we're in the 21st century and all the rest of it, dinosaurs. Remember 65 million years ago? Was it an asteroid? Was it a comet? Who knows? Also, the famous Tunguska River comet, 1908. Look what it did. That's artist's impression, by the way. Even the Russians didn't have color cameras back then. And if you still think you're safe, the Younger Dryas period, that's about 10,000 BC, the whole of the northern hemisphere's temperature dropped by 5 degrees. And there's a map of all that area there dropped by 5 degrees. So they can have a huge impact on life on Earth. So what are they? Well, we always say they're dirty snowballs, but what is that really? Well, it's water, it's gas, it's rocky dust. It's stuff that's left over from when we built up the solar system and its planets. It's the rubble that's left over. And of course, the comet, as you can recognize, consists of 3 parts, which is the head or the nucleus, which is right in there, the bright bit in the middle there. We got the coma, which is the sort of bit around here, and then this tail, and of course it's the tail that most people associate with comets. What's the size of the nucleus? Well, it's about the size of a Rocky Mountain, 10, 15, 20K diameter or so. So they're quite big, especially if it hit the Earth. The coma, well, UV photons from the sun essentially ionize the gas that's escaping from the comet, and it makes like a magnetosphere, like an ionized ball of gas around the nucleus. And then the solar winds and the magnetic field lines, the ionized particles around the comet just follow those, and you get this huge tail going out, and eventually it reconnects. But where do they come from? Okay, this is a picture, not to scale, but here is the solar system as we know it. And that's this little bit in the middle there. This around there is what's called the Oort Cloud. Now, Most of the short period comets, Halley's Comet included, which has got a period of about 80 years or so, it's what we call the short period comets, or the trans-Neptunian objects, TNOs. And they're all in the Kuiper belt, which is just beyond Neptune, and the spacecraft that just went to Pluto, which was named, what's the name of these? That's right. It's going to go to one of the TNOs in the next year or two, okay, or 5 or whenever, okay? But they only represent very few comets. There are billions and billions, as certain American astronomers might have said 30 years ago, of long-period comets. That's this Oort cloud. It's just full of them. And that's where most of the comets eventually get perturbed and we see. What are they made of? Well, here's a spectrum. This is wavelength increasing from the UV to the near infrared. This is the intensity. And you know, there's a whole series of lines there. CN, OH, carbon-2, a whole series of things. In the UV, it's even more complicated. We get all sorts of weird and wonderful. This is a spectrum that was taken by Jason McFate way back 20 years ago now. CO, CO2, CH4, ammonia, lots and lots of molecules. And also, and we'll address this later, methanol and RNA and DNA traces. Just keep that one in there for the time being. Okay, about 10, 12 years ago, NASA launched a mission called Stardust, and it was going to pass through the coma of Comet Wild. It would collect the dust samples coming off the comet, and it would return them to Earth. A very, very ambitious mission indeed. So basically, artist's impression yet again. Spacecraft comes towards the comet. That's what the comet actually looked like. And then it traps the dust, gets into that little spacecraft, and it came back to Earth and landed in Utah. And it actually did all this. But how did it capture the dust? How do you capture cometary dust? Well, they use something called Aerogel, and that's what it looks like. And I just happen to have some Aerogel here. This is very, very weird stuff. Don't open it up, but you can just pass it around if you would. That would be great. It's a very, very weird substance indeed. And the idea is that you have a whole array of aerogel blocks like that. The dust particles come in, and they get trapped in this gel. So it's a little bit like cloud chambers in atomic and nuclear physics, where you get tracks of atomic particles, but here you get tracks of dust particles. So when this came back to Earth via Utah, all those little things went to the Space Science Lab, and they started looking for tracks here. This is a piece of aerogel. Scale here, this is just 0.5 millimeter. This stuff's tiny. And you'll see here different tracks, and you can pick out the pieces of cosmic dust. So we actually have pieces of comet we know. And because there's so much aerogel there, and there's so much dust, in the good old Berkeley tradition of doing things at home, like SETI at home, we have a thing called Stardust at home. And if you go to that website, you can get your own piece of aerogel, at least from a computer point of view, and you can start seeing where the different tracks of dust is and send that information back to the researchers at Berkeley. So you can do something like hands-on there, doing some real research. So what did we find out over the last few years? Now, as I said before, comets represent perhaps the oldest stuff in the solar system. It's what was left over. It was the building blocks. So what we'd expect to see is dust from old objects. So I'll just read this out. Comets don't just consist of particles from the outer icy parts of the solar system. And that was the common assumption before Stardust went. But they found sooty dust from the innermost parts of the solar system. So how did that get there? So what it indicates is that the formation of the solar system didn't just happen way, way out and come in, but it included mixing of various dusts over radial distances close to the sun and far from the sun. This was a new idea. Now, closer to today, you must have heard of the Rosetta mission, which was mainly a European mission with a little bit of NASA help. It was a robotic mission, and it went to see this comet whose name I cannot even pronounce. This is what it looked like. Really strange looking object. And then, great thing, it actually had a lander that came down, and that landed on the surface in 2014 and took samples and the rest of the thing. Okay, now we get on to the controversial stuff. Comets. Did they bring water to Earth? I just said there's lots of ice in them. So there's Comet Hartley 2. You can see, without any doubt, there's icy things there. So a lot of people said, well, perhaps asteroids, meteorites, comets, perhaps they brought the stuff as they crashed into Earth in the young Earth. That's where all the water on the Earth came from. However, seawater isn't just H2O. Unfortunately, it also contains deuterium in that ratio, about 1 to 3,500 or so. So what did the H2O in Comet Hartley look like? Well, it actually did have about the same amount of deuterium in it. So people were going, yeah, that's it. We've solved it all. However, from the Rosetta mission, when they measured the H2O there, they didn't get that ratio at all. It was something like 3 times higher. So whether comets really brought water to Earth is still up for grabs. Who knows? At the moment, it looks as though asteroids that are residing way out in the Oort Cloud or in the Kuiper Belt were more probable bringing water to the Earth. How about the other controversial theory? And this has got to be true because it's the Daily Telegraph. It's British, so it has to be true. Comets could have sparked life on Earth as building blocks of DNA is found in space. So, Rosetta, they found amino acid glycine and phosphorus in the dust surrounding that comet. And both of those compounds are crucial to the structure of DNA, protein, cell membranes. So, that finding, even though it's not conclusive, suggests that comets might have transported the initial ingredients of life to Earth. Okay. Now that we've familiarized ourselves, or all I know about comets anyhow, what about comets beyond our own solar system? So, over the last 15 years, as you well know, a lot of research has been going into finding exoplanets. And we've got about well over a couple of thousand now, and they're mostly discovered by one of two methods. One is the radial velocity technique, which I'm sure you're quite familiar with. Basically, if you have a planet, it makes the star wobble. And if you actually measure the amount of wobble in that star, you can find out the mass of the exoplanet that's around that star. You do this with spectroscopy. The other one, which is probably more familiar for people down here because the mission has run out of aims, is the Kepler mission. And that's a different thing. Basically, you have a planet out here, and it goes in front of the star, so the star dims very slightly because it's blocking out some light. And then as it goes across, it comes back out again. And the amount of dimming, again, the area, you can make some assumptions about the type of exoplanet that could be there. So, this is a horrible slide, but I will show it anyhow. How about getting from how do stars form, how do planets form? Well, once the stars are formed from this huge nebula, you're usually left with some sort of disk of gas and dust. And from that, the big gas giants tend to form. Things like Jupiter, Uranus, Saturn. After that, you get terrestrial planets, and then all the gas and dust gets cleared away, and you're left with like what's perhaps the Oort Cloud or the Kuiper Belt. So somewhere between the initial primordial disk making these gas giants there's this thing called a transitional disk, which is like halfway between, and then you have a debris disk, which is just what's left. It's just debris that's left over from making planets. And there should be hardly any gas in that at all. It should be just dust and rubble. So why are exocomets even, why do I even bother looking at them? Well, the planetary formation theory says you've got to have circumstellar dust and gas disks around young stars. The way it works is that those dust grains eventually collide, coalesce, and they form larger and ever larger bodies. And when they're about 1 kilometer inside, they can start attracting each other through gravitational stuff. And they grow to what we might call planetesimals and eventually grow into form planets. And then once that planetary system has been formed, most of the gas is just blown away, and all we're left are these planetary building blocks. And for the case of our solar system, I've said before, that planetary debris is asteroids, TNOs, comets, whatever you like, and they're all located in the Kuiper Belt or the Oort Cloud. What about detecting them? Well, if they're believed, I always look at this. How do we, okay, if you went to a building site where a house had just been built, you'd see a whole load of rubble, bricks, mortar, and wood. So if you just saw the bricks, mortar, and wood, you'd think, a house must have been built. So similarly, it's like this. If we managed to see exocomets, gas and dust, we could probably say, there's some planetary building going on here, some exoplanets. So if you find exocomets, it's pretty convincing that you might also see exoplanets around the same star. So it's a little like the duck thing. If something waddles and quacks, it's probably a duck, and it's the same thing here. Exoducks, that would be good, wouldn't it? Okay. So how do we detect them? Well, I said they're only 25, 30 kilometers big. They're too small to image, and they're not going to cause much dimming of the central star from the transit technique that exoplanet like Kepler uses. And they're too small to make the star wobble. So how on earth are we ever going to see these things? However, the great thing is the cometary tail. As a comet gets towards the central star, all that gas gets evaporated off. And the gas is moving, and the gas is moving in front of the star. And if you go back to your undergraduate days of absorption lines, that's the classic way. You've got gas moving in front of a source of light, you get an absorption line, and the absorption line will move. So if you can see those moving absorption lines, you can sort of infer, perhaps, that exocomets are there. So this is the sort of system we look at. This is the Beta Pictoris system, which I'm going to tell you about in a minute. This is a circumstellar gas disk around Beta Pic. And as these comets come in, you notice their tails get larger and larger, and more gas is deposited in there. Now, these stars like Beta Pic, it's only 23 million years old. It shouldn't have any gas around it at all. The A star in there should have blown it all away, but it's continually replenished. And the only way it can be replenished is through the exocomet ablation. So, exocomets in the news. Who hasn't heard of Tabby's star? Or who has heard of Tabby's star? Right, and if you read all the papers, okay, does anybody want to tell you what a Tabby star is? Well, basically, it's a star that suffers incredibly huge variations in the flux that we get from it. Sometimes it goes down by 20, 30%, sometimes 5%. Seems totally random. We have no idea what it is. Some people think it's the Dyson sphere. Some people think it's this, that, and the other. But the most commonly accepted notion at the moment is that these are, in fact, huge swarms of exocomets, or in fact, or a planet that's broken up. And all that debris is dimming the light in a totally haphazard way. And the one paper that keeps getting quoted, and please keep writing things on Tabby star, is my paper, Montgomery and Welsh. So I'm very pleased about this. It's good for references. Okay. So if we look at very young stars, and what do I mean by a young star? I'm talking stars that are between 5 and 50 million years old. We might be able to find some of this debris that's left, some of the gas that's left, and perhaps we'll see some exocomet gas. Now, 90%, 95% of all the exoplanets that have been detected so far are around old stars, F, G stars, K and M stars. These things are often gigayears old. So if we see them, if we see a young planet around an A star, if we see exocomets around an A star, we're looking at the very, very earliest formation of exoplanets. So basically what you've got here is we've got the Kuiper belt, we've got this huge thing here, which is the Oort Cloud, and what we're trying to do is to find things right in this little central bit here. Way back in the 80s, there was an infrared satellite called IRAS, and it started taking images, and it looked at Vega, which is Alpha Lyrae, very bright star, first magnitude or zero magnitude star. Oops. It's going to go back. Oh, well, we'll keep going. And you may have noticed that I'm surprised that can't go back. Oh, well, anyhow. It had a huge dust disk around it. And then a couple of years later, they looked at this thing called Beta Pictoris. And you'll notice that Beta Pic, what we've done here is to block out the star, and here is the gas and the dust. It's a disk going around it. This is the first star to have something like this ever detected. It was about 1986 or so, somewhere around there. And it was viewed edge on. About 20 years after that, they actually managed to find an exoplanet around that in 2010. So, how are we going to find these things? We need a trigger mechanism to take these comets from their sort of fairly stable orbits and make them come towards the central stars cataclysmically, so it'll liberate lots of gas. And how would we do that? Well, okay, here's me at a telescope. Let's say this is a central star. This is Beta Pic. We're looking through this cold, dusty disk. And right in the middle here, very close to the star, within 1 or 2 AU, is this warm gas disk. So we will, if we're looking through there, we just see that. That's the circumstellar gas. Now, if a whole load of comets come along and go around there, all that gas will suddenly start being evaporated off, and you might see this little tiny little extra little blip on the side. So there is no exocomet, just a circumstellar gas disk, and here is the circumstellar gas disk and an absorption line there due to the evaporating gas from the exocomets. I assume most people know what absorption spectroscopy is. If not, basically it's just gas that's taken out of a system, and this signal here, this is flux against wavelength. We'll show you a bit later on. So again, just to show you, got a comet coming in, and it goes round. We look here, it's moving away from us, so you get this little red-shifted component to the circumstellar line there. And if we did it the other way, what if the comets are coming in this way? They're coming towards us, so we get a blue-shifted component here, and that will move. So which spectral line should we look for? Well, for many, many reasons, and I guess the original one, it was pure luck, they looked at the calcium-2 line at 3933 angstroms. That's essentially in the ultraviolet. You can get it from the ground, and they looked for changes in its shape as a function of time. And this was a classic paper of 1986, which was done by the French. This huge line here is a stellar line. This is from Beta Pictoris. This is formed on the surface of the star. And this narrow black line here is the circumstellar gas disk. That's the stuff that's within an AU or two. Then they looked at the next light, and look, that profile's changed. And then they looked on all these dates, and they kept seeing different things. What could that be? And, well, it could only be exocomets. But there might be a whole load of other reasons. How do you know it's exocomets? Well, those weak absorption features move far too quickly. Sometimes they can change within 2 or 3 hours, right? And that could not be due to, let's say, some interstellar gas going in front of the star. It just doesn't change on those short time scales. It's nothing from the star. It can't be anything that's being shoved out in a stellar wind, because A stars have very weak magnetic fields. They don't do stellar flares. They don't emit stuff. And most of these little absorptions are called FEBs, falling evaporated bodies. Only the French could come up with that. FEB, okay? So most of these little absorptions move from positive velocities to negative velocities, which is consistent with the way a comet would fall towards the central star. And there's a guy here called Burst who's written 23 papers on modeling how these things happen. So I think we're pretty well on firm ground. Also, the natural width of the spectral line could only be from a circumstellar gas and not interstellar or anything else. Okay, so that was 1986. What's happened since 1986? Well, after the discovery around Beta Pic, said, hang on a second, why don't we have a look at similar stars? See if there's anything happening there. We'll do the calcium line. We'll see if it changes. We'll go from night to night, get a whole load of time on telescopes, and let's see what happens. As I said, the work is mainly carried out by the French at the Institut Astrophysique de Paris. And this was a paper in 1990 on a star called HR10 by Henri Lagrange. And you'll see here that there's the stellar line. Remember the Beta Pic thing? There's the big stellar line. And there's the central circumstellar line, but no FEB that night. They looked again, and look, it changed. And that was something like I missed October, and this was August. So over 6 months or so, 7 months, something changed. So that was also said, okay, it's exocomets around there. Now we come to the lost years of the exocomets. What happened between 1990 and 2010? Well, only one more star was found that had these FEBs, the falling evaporated body. And that was discovered totally accidentally by me, because I was doing a project mapping the local interstellar medium. And it just so happened that I found this weird spectrum. I looked at it the next night, and it had changed. And then I go, perhaps it's an exocomet, and it's an A star. And true enough, that was it. So up till 1998, only 3 stars had exocomets around them: Beta Pic, HR10, and 85905. And this, I believe, was the data that I took January 24th, November 17th, January 25th. So between one night, it went from that shape to that shape. Note how the gas has moved from there, right, to over there, just as you'd expect, going from positive velocities to negative velocities. Well, after 1998, that's when exoplanets came along. Who the heck wants to bother looking for exocomets? So all the dollars, all the grants, everything else went, and all the telescope time, all went to exoplanets. And I said, okay, I'll just keep on mapping the local interstellar medium. So I gave up on this. However, you should never stop doing things. In 2010, I published a paper which was the first three-dimensional map of the local interstellar medium, the distribution of gas there, and I needed something else to do. Well, I wasn't going to get any money on interstellar research because all the money was going to exoplanets. So I said, okay, let's resurrect exocomets, see if we can get some money. And yes, we did. But how do we detect them? So we said, well, okay, perhaps they're all like Beta Pic, all A stars. They should have a dust disk. By this time, lots of other satellites had been up and said, oh, look, some of these A stars have got big gas and dust disks. They've got to have high stellar rotational velocity so we can see them edge on. They've got to be spinning fast. And we need high-resolution spectroscopy. Okay, now, unfortunately, a lot of the spectrographs had been configured to do exoplanet research, so there wasn't many left. And there's certainly, the way you do this is you look one night, you look the next night, you look the next night, and you look the next night. And see if things will change. It's very difficult to get telescope time saying, give me 5 or 6 nights just to see if anything changes. However, we persevered. We went to the McDonald Observatory in Texas, and we looked at this star called 49 SETI, which is an A star. It's about 20, 30 million years old, and it's fairly near. And look what we got. We got the big stellar line, just like Beta Pig, HR10 and the other one, and the circumstellar gas disk there, the little there, but no FEBs that night. So what I did here, I just fit that, and what we normalize it. So that's what the circumstellar line looks like, and it's got a little thing there, but what is that? So the way we do this, we look night to night and look for changes in the shape of the absorption line. And what we want to see is these absorption events that are at velocities, preferably positive velocities, away from the central line. And here, I believe this might work. Okay, did you see that? It moved. That was over a period of 3 nights. There. I don't know if I can get this to go back. No, I can't. Oh, well, you'll have to believe me. Okay, I'm going to show you some more. This is another star. It's an A-type star. Nothing there. There's the central circumstellar line, the gas disk. Nothing's changed. 2 nights later, nothing's changed. 4 nights later, ooh, where did that come from? And you go, that's too small to be true. I don't believe that. So let's do it another way. Hopefully you believe this. We get together nights 1, 2, and 3 and average them, and then we do overplot it with that one with a little tiny bit there. And I think you'll say that that is statistically significant. It is by about 4 sigma for those who are interested in that sort of thing. So there's another one we've got now. And then here's another one. This one just come out in a paper. Here, this is the interstellar, in this time there's interstellar medium and circumstellar gas there. That actually does change a little, but this is a thing that really changes. This thing that says EW is what's called the equivalent width. It's just an amount of gas that's being absorbed. And I've colored it in so you'll note. And I think you'll agree that all that black there is significantly different to all the black there. Here it's in 2 little lots. Perhaps this is more than 1 exocomet. This is a swarm of exocomets coming in. And that is different to that one there. Again, we're back now 2 or 3 years later. This has gone way down. Then it goes way up. And it splits in 2, splits in 2. So these are different exocomets coming in. Now, the great thing about exocomets is because they destroyed, once you've observed them, nobody can ever test your theories again. It's the perfect scientific thing. The downside is you don't get your name associated with it. There's no Comet Welsh because Comet Welsh dies. In fact, all Welsh's comets die. And we've got another one. This one is really quite remarkable. We did it first night. There's the central absorption. And we got an absorption event here and another one there. We went the next night, and this thing had moved. Or in fact, this one had probably moved to here. So this one there is this little bit there or that bit there. Things are moving. By the time you get the next night, it's all gone. And it's all gone the next night. So sometimes you see them, sometimes you don't. Hence the clever title to the talk. Now you see them, now you don't. Okay, what about other wavelengths? Well, you got to use Hubble because it's there. Okay, and also the ultraviolet region is the most rich region, spectral region of astrophysically important lines. So we got some time to look at 49 SETI at 2 epochs. They're not going to give us 5 different times on Hubble. You get 2, one now and one whenever they can do it. Oops. And so this is what the stuff looks like. Notice we're way down in the ultraviolet here, 1,300 angstroms. The red is one visit, the black is another visit. You notice here, this is a spectral line, nothing changes. Here, big changes. This is carbon 4. This is a high ionization line. Here, carbon 2, big changes again. Notice it's in the red part of the spectrum, just like in the calcium line. And here again, some unidentified lines also changed. So we then went to look at CO. This is warm CO. And to our great surprise, this is where the CO should be, and this is what we predicted it should be. It's just not there. So we looked at another line. This is again with Hubble stuff. This is carbon-1. This is a very neutral gas, very cold gas. And we measured the amount of carbon-1 there. And we found that its elemental abundance is way, way higher than that seen in the solar system. So the exocomet gas around 49 SETI is very different to cometary gas in our own solar system. Now, because we're talking Hubble time here, at the moment there's only been 2 stars that have had observations of exocomets. So I can't really say anything really definitive about it. This is Beta Pig, and this is essentially, these are all the different elements, carbon, oxygen, magnesium, and this is what you might as well say the abundance of what it's like in the solar system. And you'll notice it's mainly just like 0 means it's the same. Here, it's 18 times the carbon to oxygen level. So if there are people in the Beta Pix thing, they're probably really rich in carbon. Also, we've looked in the infrared, and we see emission lines there in the infrared telling us there's cold carbon-2 there. Okay, are all exocomets the same? Here's a letter that just came out a couple of years ago. Some guy looked at, he got a lot of time to look at Beta Pig. He found 6,000 absorption events over a period of about 3 or 4 years. And he did some analysis on them and found that, in fact, there were 2 different types of exocomets. And here's one of the spectra. Remember, here's the big stellar spectrum. There, look at the black line. That's the central circumstellar. But he also saw sharp lines and then really broad and deep lines. Again here, a sharp FEB, a sharp absorption, and a narrow but elongated one. And what he found out, that the shallow absorption ones, that's this type here and this type here, comes from old gas, and it's been depleted from all its volatiles. And if you remember, go back to the Stardust results. Remember that we had a mixture of dust in Stardust, some from the outer solar system, some from the inner. And it looks as though we're seeing similar, but not the same, but similar sort of thing towards Beta Pig, 2 different types of exocomet. So, this is about all we know at the moment. We've only detected exocomet gas in young A-type stars with debris disks. That's all we looked at. And we've seen 20 of them. 17 of which I've looked at, have detected. So I hold the record. But who cares? We've looked for exocomets around F, G, K, and M stars. We haven't been able to find them at all. They're too old. All the cometary activity seems to have died right down. Or we've just been really unlucky, because on the 4 or 5 nights we looked, nothing happened. Remember, on Earth, think about how often do we see comets on Earth? Yeah, we're lucky if we see 1 or 2 a year. Okay, and we're old. We're 4.5 billion years old. And so are some of these stars. So it's probably not surprising we don't see any exocomets around these older stars. From the 2 or 3 cases we have, their elemental compositions differ from the gas and dust in our own solar system. And as I said, the research is still in its infancy. 20 systems have just been discovered. Most of them are discussed in this lovely paper by myself and my colleague there, Sean Montgomery. And we just got back from ESO, European Southern Observatory, in November, where we were given 3 nights. It was a Monday, Wednesday, and Friday to look at, I think we looked at 23 A stars. And I just finished some of the initial analysis, and I think I found another 5 or 6 exocomets. So we're getting up there. We're getting up to 25 or so. And with that, yeah, I think that's it. Thank you.
Thanks a lot, Barry. So the floor is open for questions. You sample is here.
Yeah, cheers.
Okay, I'm going to start over there.
What about water and OH lines? Can you look in any part of the spectral region where you can get the resolution that you need?
You can see the water lines, but you don't know whether it's probably not from the inner stuff. It's more likely it's in the outer gas. So it's not really telling us anything about exocomets. It's just telling us about the circumstellar cold gas and dust around A stars.
There was one question here.
Hey, Barry. So in some of the stars, especially one, I can't remember its name, it looked like the middle line, the main circumstellar line, was varying a lot.
Yeah, it changed, yeah. And what happened, let's say that's the central line here, and you've got an FEB, it moves. And in velocity space, it adds gas. Even though it's not part of the circumstellar line, it's at the same velocity. So it looks as though its profile's changed. And then sometimes it moves to negative, and sometimes they just go into the central star. So it's not unusual to see this central line change. It depends on how many comets are coming in. Sometimes they just don't get there. Sometimes they get there and go past. Yeah.
Hi. So you're looking at all different kinds of stars with all different kinds of compositions.
Not really. No, just A-type stars.
Just A-type stars.
Yeah.
Okay.
And they're fast rotators, and they've got to have a debris disk.
Okay. And so you're seeing. Are you seeing any differences in these early solar systems from ours, other than like they're way more common,
they're way more common?
Are there any other characteristics of the comets that are different from our comets?
Well, just the abundances. At least the two or three we have. That's to say, we've only got 2 or 3 examples because it's difficult to get Hubble time. And it's not just one observation. You want to look 2 or 3 times.
So that brings me to my question.
Yeah.
So Hubble is reaching the end of its lifetime. I mean, there will not be in Hubble in 10 years. So what's the future of UV spectroscopy?
Of UV spectroscopy? Well, believe it or not, we just got a letter asking us to think about a 5th servicing mission to Hubble. Exactly. Well, way back, okay, when the shuttle had its problems, they were thinking of doing a robotic one then. In fact, they built up a thing at Goddard. You could do a robotic change-out. It's very risky. It all depends on what happens to JWST next year. I mean, NASA's put all its eggs in one huge basket, $9.5 billion worth of money. If that fails, who knows?
One question here.
You measure velocity distributions.
Yes.
Can you learn anything from your velocity distributions which cause, of course, the heating of the comet that gives off the tail that tells you about the structure of the comet or its overall composition, because it's got to absorb the energy, got to produce the gas that you see?
You can. Of the 20-odd papers I referred to by this guy called Burst, that's exactly what he does. And I didn't want to go into that because of the audience probably would have fallen asleep. I refer to those. There are 20-odd papers, B-E-U-S-T, Burst. Yeah.
Is there an asymmetry in the velocities as viewed from Earth? You said they go from
that's
negative
because
to positive.
Most of them are falling towards the star. Therefore, they're moving away from us. Therefore, it's positive. Yeah.
But they could be falling.
But they
towards
could
the
be
star
coming
from
the other way.
side.
Yeah. Well, it's also the way we choose them, which is in fast rotators and viewing them edge on. It could be just the total select.
They should still be symmetric.
It should be. Yeah, that's right. It's our selection effect. That's what we see. I would say 90% of the absorption events we see have positive velocities. Only 10% have blue, and it's the way it is. And it does come out of some of the papers by this guy called Burst.
I have a question. What about extending this study at other wavelengths? I mean, to understand comets on Earth in our solar system, we have been studying comets in UV, far infrared, mid-infrared, etc. So is there a group that is working now on the same kind of analysis, but for the mid-infrared, for instance?
Not that I know of, no. There's myself and one other, and I think there's one other group who are looking at exocomets. It's because, well, okay, To be crude about it, there's more money in exoplanets.
Because what, sorry?
There's more money to be had looking for exoplanets than exocomets. And you go where the money, that's life. You go where the dollars are.
Okay, well, no more questions. So before we close the floor completely, I'm gonna give you this wonderful gift from the SETI Institute. I know. So you semi-retired. I don't know exactly what it means, but
so I get a senior discount now. That's good.
So I hope you're gonna use it.
Oh, definitely, definitely. Thank you. Thanks very much indeed.
Thank you very much for coming. Thanks.
Thank you.